All right, let's get started. So we did number 1 the other day. Is that good spacing on the board? I can't tell. Yeah. So we did number 1 the other day. So let me get rid of this one. And let's look at number 2. Okay, let's look at number 2. Lucas, can you read number 2 for us?
An astronaut of mass 80 kilograms carries an empty oxygen tank of mass 40 kilograms. He throws the tank away from himself with a speed of 2 meters per second. With what speed does he start to move off into space?
So here's our astronaut. Okay. And what is he holding?
An oxygen tank.
An oxygen tank? How's that look? Is that good? And what's he going to do to it? He throws it away from himself. Now, here's the question. If he pushes it away from himself, he's applying a force that way on the oxygen canister. What does the oxygen canister then do to him? It pushes him back, but with more or less force. You'd think it's less because it's smaller, but what's really true? It's the same force. Remember, Newton's third law of force pairs say that whatever force you apply on an object, it applies the same force back on you, right? But the result is less, okay? The result is less because if we look at the after result, okay? Our astronaut is going to be moving backward. So he's going to be moving this way. And the oxygen container is going to be moving this way. Is that cool? So let's do the energy chart first. Now, we won't be able to do the whole energy chart because we don't necessarily know everything yet. Oh, what is happening today? Did you see that? So we got the astronaut in the canister. I feel pretty good about that. Is anybody moving to begin with? No. So we actually don't have any kinetic energy to start. Are we going to have kinetic energy on the backside? We totally are, but we don't know how much it is, so just leave this for now. Is that cool? All right, let's do the momentum charts. I should have done them underneath, but I drew my picture too big, sorry. All right, this is the mass, this is the velocity, this is the mass, this is the velocity. Okay, so what's the mass of our astronaut? 80? And what's the mass of our canister? 40?
Kilograms.
So how big should my red line be compared to my blue line? Half, right? Does that look okay? Cool. I'm going to draw them over here the same way because we still got our same pieces here. All right. What piece of information do we know about the after? It says, yeah, go ahead. Say it again.
Your area is going to equal 0.
Yeah. So what do they tell us about the after, though? What do they know? We know there's a speed after. Which one is it?
2 meters per second.
The canister's moving at 2?
Yeah.
Okay, that's good. So when I go to draw this, which way is my canister moving? To the right or to the left in my picture? Moving to the right at 2 meters per second. I'm going to draw that. Now, it doesn't matter how big 2 is, as long as everything on here is relative to everything else on here. So this is 40 kilograms, moving at 2 meters per second. So what's the total area of this bad boy? It's plus 80. Is that cool? Because I did 4 times 2? 40 times 2? Now, this is what Michaela said. I said, well, what do we know about the after? And she actually skipped ahead. So tell me, let's look at the before picture. What do you notice about the before picture? Is there any area represented? The answer is no. So what does that tell you about the total momentum then? The total momentum, so P for momentum is equal to 0. What does that tell you about the after total momentum? What does it have to be?
0.
Also 0. That's the point. So here comes the cool part. If the canister has a total momentum of plus 80, what has to be true about the astronaut? What does his momentum have to be? It's got to be negative 80, correct? Because plus 80 and minus 80, so what does that mean about him? Which way does he have to be moving? To the left, how fast?
1 meter per second.
1 is correct. And if you notice these, within my ability to draw them, it's twice as tall but half as wide. This one's half as tall and twice as wide. You add those two together, you get a 0, which I love. And now we can go back and we can fill this in. So, what is the kinetic energy of the astronaut? 1/2, his mass is 80, his speed is 1 squared. 40 joules. The kinetic energy of the canister is 1/2 of 40 times 2 squared. 4, that's 80 joules. Is that cool? Now, we still have a slight problem. Okay? We still have a slight problem because I'm looking over here and what's my initial energy situation? There is none. But on the after side, do I have a ton of energy? I do. I got 120 joules worth of energy. Where did it come from? The astronaut put it in because he was the one doing the pushing, correct? So we're going to go like this. We're going to say, into the system, oh, what was that? So the astronaut, we say he did work on the system, but what that just really means is he added 120 joules of energy to the system. I love this treatment because it's helping us kind of apply all our understandings from everything we studied. We got a Newton's third law force pair in terms of forces. I mean, think about it this way. Why does the canister move faster than the guy?
Because it's lighter.
It has less mass, right?
Yeah.
Right? Because they're not on a planet or anything, it's not technically lighter because lighter is a measurement of the gravitational force on it, right? But less mass, so it has a greater acceleration, greater speed. We understand our energy concept, where the energy came from, how it's represented, and we have our momentum concept, where we say the total momentum before equals the total momentum after. All of these together give us a much deeper understanding of the world around us. Right? Does that make sense? All right, that was 2. You want to do 3? Was that 2?
Yeah, that was
I love 3. I think 3 is a hard one. But I think it makes a ton of sense. All right, so here's the guy. How's that look? Is that consistent with what it says? All right, so we know a couple things. For example, we know that the mass of our arrow is 0.5 kilograms. True? And the velocity of our arrow is 18?
It's 30 on that one. It's 18
Oh,
on the
oh, it's
other
18 on
one.
the far one. Sorry. Thank you. Afterward, the mass is still 0.5 kilograms, but it's slowed down, right? What about the melon? What's the mass of the melon? Oh.
2.
And right here, its velocity is 0. The mass is still 2 kilograms. And the question wants to know, how fast is it moving? So one of the things that's cool about this is, what do you notice about the arrow? Did the arrow slow down? It totally did, right? So would you say then it lost momentum? I would. Where did all that momentum go?
In the water.
It had to go into the melon, right? So the idea that we're losing momentum, we have to know it goes somewhere because the momentum is always the same before and after. So let's do the energy first. So I got the arrow, I got the melon. Feel great about that. Okay. Let's do it up. Let's put our masses on. What's the mass of the arrow? Half? And the melon's what? 2? 3? 2. So how many times longer is it?
4.
Right? The reason we use the diagrams like this is it helps us relate just our visual understanding of things to our mathematical understanding of things. So when I go to put this in, it's moving at 30 meters per second to start. So it's half a kilogram, moving at 30 meters per second. So what's the total area here? It's plus 15, right? But then, when I look at it over here, what's the speed now?
18.
It's 18. Now it's a little bit more than half, but it's definitely less than before, true? So I have 18. So what is the total area now? It's only 9, right? Because I got half of 18 is 9. It was 15, now it's 9. How much is lost?
6.
6 is lost. Where did it go?
No.
It went into the motion of the melon. So here's the cool part about this. All right? Watch closely because this is like magic. What is the size of the height of the melon? 2 kilograms, right? Well, if I know that the total area has to be 15, and I have 9 here, I know that the area of this one has to be 6. So if the height is 2 and the area has to be 6, how wide does it have to be? It has to be 3, that's correct. And a 3 is a third of this 9. And so that tells you that the speed must be 3 meters per second. So using the graphical representation in the pictures, it's actually not too challenging to see like, oh, if I know my total area has to be 15 and I have 9, this area has to be 6. Area is length times width. Just use your brain a little bit. So fun. Let's do the kinetic energies real fast. So I'm looking over here. The kinetic energy here is 1/2 the mass times the speed squared. 30 squared, that's got to be 900. Half of 900 is 450. Half of that is 225. Is that cool? What's going on over here? I got 1/2 the mass of the arrow times the new speed, 18 squared. Oh, I don't know what 18 squared is. That is outside my everyday math. 324, 162, 81. And, but the melon is now moving also. One half of 2 is 1, so that's 9. I actually really like this because if you look at this, this arrow had 225 joules of kinetic energy, and now it only has 81. That's not very much, right? It's less than half. And then how much does the melon have? Basically, just 1/9 of that. So did I lose some? Certainly I did. How much did I lose? 225 minus 90?
135.
135? How do you feel about that? Pretty good? It's super easy when I do it, but I want to make sure that matches your understanding. We good to go here?
Yep.
You guys are awesome. Thanks for putting up with this. All right, so we got a football player here. running this way. He's going to be met by another football player coming the other way. Is that cool? All right, and so what's going to happen is they're going to hit each other, and we're going to see what happens. Have you heard that? Okay, so we have two. We got the here, I'll do it. So the quarterback is the one with the football. Okay, he's running with the football. I know this is annoying because you have to know something about football to understand this problem. Sorry about that. Okay. This guy, what's his mass?
75 kilograms.
And he's moving this way at.
6 meters per second.
I'll put that in here. Is that cool? The other guy is 100 kilograms, so he's more massive. He's going at 4.5, but which way is he running? To the left. So what's true about his velocity then? Negative when I go to put it on here. Here's what I love about this problem. We just diagrammed it up, but all of a sudden there's this cool understanding. Like, what's the total area of the green? It's negative 450, correct? What's the total area of the blue? It's positive 450. So then, what is the total momentum then? It's 0. How cool is that? So what's going to happen then? What's going to happen when they hit then? If the total momentum is 0, what does that mean about them? They just hit stick and